In a prior video lesson from this unit, we applied Kirchhoff's loop rule to an RL series circuit, and we were able to state that EMF minus resistance times current minus inductance times rate of change of current has to equal 0. And by solving that differential equation, we derived an expression for the way in which current varies as a function of time. And we said the current is equal to some maximum value times the quantity 1 minus e to the negative t over tau, where tau in this case is equal to the inductance divided by the resistance. So the effect of an inductor in a circuit is to limit the way in which current can grow. In other words, it affects not so much the current, but the rate of change of current. So that a graph of current versus time grows asymptotically towards some maximum value. And of course, that maximum value is just governed by Ohm's law and is equal to the battery EMF divided by the circuit resistance. If we put tau on the time axis, then it intersects our curve at about 63% of the maximum current. Okay, well, in this video lesson, we're going to investigate a different type of circuit. Instead of the RL series circuit, let's take a look at an LC oscillator circuit. So here we have a two-way switch that can either be moved to position A, in that way connecting the capacitor to the battery so as to charge it. Notice that we have no resistance on this part of the circuit. So if we do put the switch in position A, the capacitor will charge very quickly. And then once the capacitor is charged, we can move the switch into position B and let the capacitor discharge through an inductor. The behavior is a bit surprising. It doesn't cause a quick discharge that ends. What happens is the capacitor starts out with positive charge on the upper plate and negative charge on the bottom plate because of the way it was connected to the battery EMF. And when the switch is indeed moved to position B, the capacitor does discharge, but then it charges up again and reverses the polarity on the plates. Then the charge goes back to 0, and the plates return to their original value, and the behavior, somewhat surprisingly, or perhaps not, is very similar to the behavior of a mass connected to an ideal spring on a frictionless surface. So if a mass starts out at its equilibrium position and then is pulled back to some positive amplitude and released, it doesn't just move and return to its equilibrium position and then immediately come to rest. It overshoots the equilibrium position and then gets compressed to negative the original amplitude. Then it moves back to equilibrium position, but it doesn't stop there. It goes back to where it returned. So that's somewhat the behavior of the capacitor. When it's moved, when the switch is moved to position B, it discharges. It's kind of like going to an equilibrium state, but then it charges up again in the opposite direction. That's sort of like having the mass become compressed against the spring instead of stretched, and then it goes back to 0 charge, which is like coming back to equilibrium. I think you get the comparison here. So let's see if we can derive an expression just purely mathematically that explains why that happens. So again, we'll apply Kirchhoff's loop rule. Or how about this? Maybe a little different than Kirchhoff's loop rule. What if we just say we have a point A, well, I've already labeled A and B as the switches, haven't I? Let's call it point X and point Y. So if I measure the electric potential at point X and the electric potential at point Y, we can see that as either being a way to state the voltage across the inductor, V subscript XY is equal to the voltage across the inductor, but then again, it's also the voltage across the capacitor. And so at any given point in time, the voltage across the inductor and the voltage across the capacitor have to be equal, but that's really just the nature of anything that's connected in parallel, right? So if the voltage across the capacitor equals the voltage across the inductor, then we can say whatever the instantaneous value of charge is on the capacitor divided by capacitance, that's the way we calculate voltage, right? That has to be equal to negative L times whatever the instantaneous rate of change of current is equal to. But then again, current is the flow rate of charge, so di dt can be replaced with the second derivative of charge with respect to time. So let's do that. Let's call this negative L d2q dt squared. This is a bit of a head scratcher. So let's just say the charge that exists on the plates is a function of time. Very much like the position of a mass on a spring. Once you pull it back and release it from rest, the position is a function of time. Always changing, right? As the block moves back and forth, compressing and stretching the spring, the position is always changing in time. Once the switch has been moved to A to fully charge the capacitor, and then we move the switch to position B, the amount of charge that resides on the plates varies as time passes. So this expression is telling us that that function that describes how charge varies in time is directly related to the second derivative of that very function. So you have to think to yourself, what type of equations can I take the second derivative of and just get back that same equation? Let's multiply both sides of this equation by c. So we get q is equal to negative LC times d2q dt squared. Or, how about this? What we're saying is the second derivative of charge with respect to time is negative 1 over LC times charge. You see what I'm saying? Find an equation for which we can take the second derivative, and it just gives us back a constant, actually a negative constant, times the very function that we're taking the second derivative of. Well, I'm going to wager a guess and say maybe Q equals, how about e to the ct? I think that's a equation that when I take the second derivative, I get back a constant multiplied by the original function. Let's see, what's the first derivative? dq dt would equal c e to the ct. So the second derivative of charge with respect to time would be c squared e to the ct. But e to the ct itself is q, so I came close. I found a mathematical expression for q. When I take the second derivative of it, it spits out a constant. Well, any constant squared is itself a constant, right? Multiplied by the original function. Well, that's almost what we were going for, except I was hoping to get a negative constant. Let me wager another guess. Let's guess that q equals e to the negative ct. Then the first derivative gives me negative some constant e to the negative ct, and the second derivative gives me, oh shoot, when I take the second derivative I'm going to have a negative of a negative, so I'll be back to positive constant squared e to the negative ct, where e to the negative ct is q, so same case, I'm taking the second derivative and it's giving me back my original expression multiplied by a positive constant. Let's try another guess. Sine and cosine are functions that when I take the second derivative, I get back the original function. So let's guess that Q is equal to, how about cosine of some constant. Instead of calling it C, this time I'll call it omega times t. And the first derivative gives me omega times negative sine omega t. And the second derivative gives me negative omega squared cosine omega t. But we notice that cosine omega t is Q, so we've done it. We've found an expression for Q such that if we take the second derivative, it gives us a negative constant times Q. Now let's just see if this matches our initial conditions. If I were to throw the switch into position A, then what's the initial charge on the capacitors? And the equations say Q equals CV, or in other words, Q naught would equal the capacitance times the battery EMF. But this guess says at time t equals 0, well, then we'd have cosine of 0, which gives us 1. Oh, this would say Q naught equals 1 coulomb. But it's not exactly 1 coulomb. It's whatever the product of then let me just fix my guess a little bit and guess that Q is equal to CE times cosine omega t. Then, just to be sure, dq dt would be negative omega CE sine omega t, and the second derivative would be negative omega squared CE cosine omega t. But what is CE cosine omega t? Yeah, sure, that's Q. So we have the second derivative is equal to negative omega squared Q. Let's look at this carefully. This is the result we get for the second derivative if we guess that this is the expression for charge as a function of time. But we were hoping, if I scroll back up, we were hoping to find that the second derivative would give us negative 1 over LC times Q. So this is what we got, and this is what we were hoping to get. Well, the two of these look somewhat similar, don't they? In fact, they'd be exactly the same as long as negative omega squared is equal to negative 1 over LC. We can cancel the negatives, take the square root of both sides of the equation, and it says omega would have to equal the square root of 1 over LC. Well, let's see, omega represents what we call angular frequency. And if we're right about this, if moving the switch into position A to initially build up a charge of CE and then flipping the switch to position B to allow the capacitor to discharge through the inductor causes it to oscillate so that initially the charge is positive on the upper plate and negative on the bottom plate, and then the charge goes to 0, and then it becomes positive on the bottom plate and negative on the top plate, and the charge goes back to 0, and then we go to a full cycle where we return to the initial condition where it's positive on the upper plate and negative on the bottom plate. Then that represents a process that's cycling, and it has to happen with a particular frequency. In other words, if we were to make a graph of the charge on the upper plate versus time, let's say this represents positive charge and that's negative charge. Then at time t equals 0, the charge on the upper plate is positive. After a quarter cycle, the capacitor is fully discharged. And then after half a cycle, the capacitor has charged up in the opposite direction, so now the upper plate has negative charge. After 3/4 of a cycle, the charge is back to 0, and in a full cycle it returns to having the upper plate positively charged. Well, this is just a graph of cosine, which is what we guessed for our equation that represents charge as a function of time. So everything seems to fit together, and we can see that this is a graph that has a particular frequency to it. If we were to graph a different capacitor, maybe connected to a different value inductor, maybe the graph would have the same shape, but a higher frequency. So what determines the frequency? The frequency is equal to the square root of 1 over LC. In other words, as the inductance goes up, the frequency goes down, and also as the capacitance goes up, the frequency goes down. So increasing the value of either the inductor or the capacitor will have the tendency to decrease the frequency with which the circuit behavior oscillates. So let's take this step by step and see exactly what would happen. So in step 1, the switch had already been in position A for a while, so we built up an initial charge equal to capacitance times battery voltage. The upper plate then is positive, the bottom plate is negative, and at time t equals 0, we move the switch into position B. So let's see what would happen just a little bit later in time. Let's see, right now, the initial current is equal to 0. But now we've got a case in which the capacitor is behaving as a source of potential difference to drive a current in a clockwise direction, and then the current is going to reach the inductor, and let's see, it's going to spiral around this way. You can try the right-hand rule and see what you get. You agree with me on this? That a magnetic field would then appear, and some magnetic field lines would be self-imposed on the inductor. So that means the inductor is going to try to fight itself in a way. It's going from an initial case where if there's 0 magnetic field in the inductor, then there's 0 flux for the inductor, and once the current starts to flow in a clockwise direction, then magnetic field lines appear in the inductor, and now the flux is non-zero. And Lenz's law tells us that nature opposes a change in flux, so the inductor tries to drive current in the opposite direction. A back EMF develops, and so how about we call this point about point P and point Q in the circuit. So point P would be positive and point Q would be negative. Okay, everything's fine so far. That means the charge on the plate is becoming a little bit less as current flows in this direction. The inductor is trying to fight against that increasing current, and eventually we get to a point where now the charge on the capacitor is equal to 0. What about current? Well, when the charge equals 0, this current has then reached its maximum value, continues to flow in a clockwise direction, and now the magnetic field imposed in the inductor is of its greatest strength. If we have the max current, we'll have the maximum amount of magnetic field, which means there's the maximum amount of flux. And at the moment the current reaches its maximum value, then for an instant in time, the rate of change of current is equal to 0. So although there's a amount of flux, there's no rate of change of flux. And so all of a sudden, the electric potential at point P and the electric potential at point Q are equal, and so the voltage across the inductor is 0. But notice, if there's no charge on the capacitor plates, then the voltage across the capacitor is also 0. Well, thank goodness. Any two devices connected in parallel have to have the same potential difference. So now at this point, the magnetic field of the solenoid is going to start to collapse. And as it collapses, the current becomes less than its maximum value. So the current is now still flowing in a clockwise direction, but that current is less than the maximum current. So the magnetic field lines start to shrink. They still point in the same direction, but the flux is less than the maximum flux. So that means there's a decrease in the flux. Well, inductors, hey, they follow Lenz's law. Nature opposes a change in flux. So the inductor would like to create an EMF that tries to make the current return to its max value so that we bring back those magnetic field lines that the inductor has grown accustomed to, so to speak. So now the voltage across the inductor, point Q becomes positive, point P becomes negative, and that would tend to drive greater current in a clockwise direction. And so what happens is, even though the capacitor had reached a charge of 0 in the previous step, the imposed EMF across the inductor tries to drive current so that it starts to charge up the bottom plate positively. The top one becomes negatively charged. And so if that's the case, the voltage across the capacitor, positive on the bottom plate, negative on the top plate, and that matches the voltage across the inductor. And this process continues until the capacitor reaches its maximum amount of charge, which would just be equal to CE, the value that the top plate had initially. The upper plate is negatively charged, and at this point, the magnetic field has now totally collapsed. The current in the circuit is equal to 0, and if we were to graph all this, the charge on the capacitor as a function of time started out maximum value, positive on the upper plate, so that would correspond to this data point. And then a little bit later, there was still some smaller amount of charge, positive on the upper plate and negative on the bottom plate, and there's a little bit of current in the clockwise direction. Oh, let's make two graphs then. Let's graph current versus time. So if we graph up until this final state, what we see the charge has done is gone from its maximum value, capital Q, to some lesser value, to the instant in time at which the charge for a moment was equal to 0. And then we got a little bit of negative charge on the upper plate. And then we've reached this state where the upper plate has a charge of negative Q. And so we've really just graphed half of a cycle of cosine. And so what's happened with the current? Let's say that this portion of the graph represents clockwise and this portion represents counterclockwise. Then right off the get-go, the current started out in step 1 as 0, and then we got a little bit of clockwise current, not quite its maximum value of clockwise current. And at the instant that the charge on the capacitor was 0, the current had reached its maximum value in a clockwise direction. So if we graph all this out, we're saying the current started at 0, and then we got a little bit of current in a clockwise direction. Then it reached its greatest value in the clockwise direction, and then what ultimately happened? It started to become a little bit less than its maximum value, but still going clockwise. And finally, in our last bit of illustration here, the current had dropped back to 0. So what have we graphed here? It looks like this is just half of a cycle of negative sign. So I don't want to go through the full explanation again. You could imagine if we just reversed that process, that now the current's going to start to flow back in a counterclockwise direction. And at some point, there's going to be an imposed voltage across the inductor that's always fighting the rate of change of current. And so if we just draw in what we expect to happen for the next half cycle, we would figure that we'd return to this point, and likewise, the current would just do the same thing, but in a counterclockwise direction. Now, does this agree with our predicted equation? In fact, if we continue the graph, it just goes on, and we're really just graphing cosine. So this would suggest that Q is equal to CE. Isn't that what this Q max was equal to, right? CE times cosine of omega t. Sure, that's exactly what we guessed. And that's exactly what we've graphed based on our conceptual explanation of how this capacitor is discharging through the inductor in time. And what about current? Well, if we keep going with the graph, this just says that current is equal to some maximum current times a graph of negative sine omega t. Let's look back at our derivation here. If we guessed that charge is CE cosine omega t, well, the first derivative of charge with respect to time, that's the same thing as current, and look what we have, negative sine omega t. So I guess this means I maximum is equal to what? If this expression matches this expression, then the maximum current should be omega times C times E. But remember what omega was? Omega is the square root of 1 over LC. So there we have it. An LC circuit is an oscillating circuit as the capacitor discharges, reaches a charge of 0, overcharges in the opposite direction, and the cycle continues. And don't forget that this is just an electrical analogous behavior to the oscillating motion of a mass connected to a spring when initially pulled back to some positive amplitude and released and allowed to move in such a way that it overshoots the equilibrium position, becomes compressed, and so on.